Hello again. Welcome to our pre-lab video series. This week's pre-lab is on the empirical formula determination, part of the General Chemistry 1 laboratory sequence at York College in Pennsylvania. Let's get right to it. Your goal today in lab, or this week, is going to be to make or prepare two ionic compounds and to determine their respective formulas. A couple of bits of background. Ionic compounds generally, but not always, contain a metal as their cation and then a non-metal as their anion. In today's lab, you'll be working with zinc in one case and chlorine. So you'll make a zinc-chlorine combination. And in the second case, you'll be working with copper and sulfur to make a combination. The zinc-chlorine case leads to a very obvious conclusion. The only formula that zinc and chlorine can make together are ZnCl2. This is because zinc always has a 2+ charge and chlorine adopts a -1 charge. So when the two bond together, to balance out the amount of charge, we need 2 chlorines for every 1 zinc. So you should be able to determine the formula today of zinc chloride reasonably well to be ZnCl2. On the other hand, copper as a metal can adopt a +1 or a +2 charge. Sulfur should always adopt a -2 charge. This would lead to two different formulas, either a Cu2S in the case of copper being a +1, or a Cus in the case of copper being a +2. So that part of the lab is a little bit more of a mystery, and the real goal to see if you can first confirm our method is a good one for determining a known formula that we should get, and then seeing how well it can help us determine the formula of an unknown compound when we're not sure which one we should be getting. Now, in these formulas, these subscripts always represent the ratio of the moles of each element present in a unit of that material. And it has to be a ratio of moles or of individual atoms or ions, but never a ratio of masses. That's because each element has a different molar mass. So the objective of being able to accomplish the formula of a compound relies on your ability to determine how many moles of each element are present in a particular sample. Those moles, though, will be derived from the masses of the elements that you have present. Right? Let's go through the pre-lab exercises, because this week's pre-lab really do set the stage for the calculations that you'll be doing in the lab. The first pre-lab question speaks about the mass percentage in sulfur trioxide. So sulfur trioxide, if you haven't yet learned naming of molecular compounds, would be SO3. In 1 mole of sulfur trioxide, we would have 1 mole of sulfur and 3 moles of oxygen, for a total mass of 80.06 grams. So the percentage of sulfur would be the mass of sulfur divided by this total mass, multiplied by 100%. So a mole of sulfur, 1 mole of sulfur, because I'm assuming I've selected 1 mole of the entire compound, so that would contain 1 mole of sulfur, is about 32.06 grams, divided by our 80.06 grams, times by 100, 40.0% sulfur. Now, given that the compound only contains 2 elements, the remaining 60% must be from oxygen. So we've quickly solved for that. But we could verify that with a quick calculation. We have 3 moles of oxygen so that would be 3 times the 16 grams per a single mole divided by the total 80.06 times by 100, and we sure enough do get 60.0% oxygen by mass. Mass percentage is an interesting technique. It's particularly useful in industries where you might be mining for a material, and when you dig up rocks, you might be concerned with what percentage by weight, right, or mass, is the element of your interest. If you're looking for copper and copper mining, or if you're looking for tin, those things are going to come out of the earth as oxides, and so the higher the mass percent of the sort of the non-oxygen element, the greater amount of that you're going to be able to extract when you break down those ores. Okay. Our second pre-lab question, a little more relevant to what we're doing in lab today. A different way of determining an empirical formula is from percent composition data. Here we, in the first question, used a formula to determine percent composition. We're going to work backwards from percentages to a formula in this second example. So if a compound is 68.2% carbon, what we're going to do is assume that we have 100 grams of compound. For every 100 grams of compound, 68.2 grams would be carbon, since this compound is 68.2% by mass carbon. We also would have 6.86 grams of hydrogen, 15.9 grams of nitrogen, and 9.08 grams of oxygen. To come up with the formula, we need the ratio of the moles, again, not the masses, because each of these weights or masses represents a different number of particles. So we need to be speaking the same language, the language of moles or particles, before we make that comparison. So each of these masses can be converted to its respective mole quantity by dividing by the molar mass. 1 mole of carbon is 12 grams. 1 mole of atomic hydrogen, 1.008 grams. 1 mole of atomic nitrogen, 14.01 grams. And 1 mole of atomic oxygen, 16.00 grams. So I have 5.68 moles of carbon, 6.81 moles of hydrogen, 1.13 moles of nitrogen, and 0.568 moles of oxygen. At this point, we technically have our ratio of moles, but we're not allowed to write a formula with these decimal subscripts. We want whole number subscripts. So we're looking for a way to scale up or down these decimals to give us whole numbers. And the easiest way to achieve that is to divide by the smallest number of moles, which in this case is oxygen. So we divide all of our numbers by this. This ensures that our smallest whole number is 1, and every other number will be larger than it. In the case of nitrogen, we get pretty close to 2. In the case of hydrogen, we get pretty much 12, and we get right on 10 for carbon. So our decimals become C10, H12, N2, O. And now we have all whole numbers for our compound formula. All right, the last pre-lab question is definitely related to the calculations you'll do in lab today. So I hope you make a good copy of this one and keep it to guide your work during the upcoming week when you do your lab report. So we've taken a sample of strontium and reacted it to form strontium oxide. We have the weights of the sample before and after. So we have before 0.650 grams of pure strontium. After our process, we have 0.774 grams of our compound. The first question, what is the mass of oxygen? Well, the total mass of the compound, right, must just be the mass of the strontium plus the mass of the oxygen that we added. Therefore, the mass of the oxygen is simply the total 744 minus the initial 650, or 0.124 grams of oxygen were incorporated into this compound. How many moles of each element are present? We can take our 0.124 grams of oxygen times 1 mole over 16 grams, just as we did in the previous problem, to get 0.00742 moles of oxygen, and our 0.650 grams of strontium times 1 mole of strontium divided by 87.62 grams, its molar mass from the periodic table. And we also get 0.00742 moles of strontium. Sorry, I've noticed a little error. I switched the numbers. For oxygen, this number is actually 775. So now, to get a whole number, we divide, and this is now part C, what's the ratio? We divide by the smaller number, 0.00742. It's definitely going to give us a 1 for strontium, and this is 1.04, so it might as well be 1. So our ratio is 1 to 1 for part C. And lastly, our formula is SRO. So this is how you'll determine the empirical formulas of your compounds today. You'll weigh a sample of a metal, zinc for example, in part 1 of the experiment, before you begin a reaction. You'll complete a reaction which will incorporate chlorine into the zinc compound, and you'll weigh the sample afterwards. Then you'll simply go through this little process right here, subtracting the mass of zinc from the total mass will give you the chlorine mass, converting each mass to moles, and then finding the lowest whole number ratio will give you the chemical formula. This is quite a fun experiment. It's the first time you get to do some real chemistry, and let me show you some of the equipment that you'll be using and talk about some of the safety concerns that we have in this week's lab. First of all, we are going to have hydrogen gas being produced at one point during our experiment today when we react zinc with hydrochloric acid. Please be extra careful that you are not conducting this reaction anywhere near anyone who is using the Bunsen burner in the lab. Hydrogen gas is of course flammable, and it could turn into a bit of a fireball or a source of a fire if those vapors were to catch fire. So we're going to make sure that you're working away from Bunsen burners during that portion of the experiment, and that you're in the fume hood and we're drawing those hydrogen vapors out of the lab as quickly as possible. The other real concern that I have today, or this week, is the temperature of some of our materials. We're going to be heating things up with a Bunsen burner and a hot plate, and a lot of our supplies will get very hot to the touch, and you must be careful that you don't just grab something with your hand and burn yourself pretty badly in those cases, especially in the case of the Bunsen burner. Now, the zinc portion of the reaction will take place in an evaporating dish. Just a little porcelain dish that you can put the zinc and hydrochloric acid into directly, and then you can gently heat this over top of a steam bath, I believe, to evaporate off the liquid. When you're handling this when it's hot, you're going to want to use a pair of crucible tongs. Okay? They have a funny little shape in the stems of the tongs. You can just grab this pretty safely and securely with the tips of the tongs. Okay? And this is not designed to sit like this. It's a little less stable. You could try that, but you might want to practice before you begin. See? So you might want to practice before you begin the experiment as to how hard you can squeeze any one of these pieces of equipment and how you can safely hold it, whether you're more comfortable this way. As a backup, I don't have one here, you can use what we call a hot hands. It's a little rubber piece that you can stick your fingers into that you could hold underneath as a backup in case this should slip. The second reaction between the copper and the sulfur will take place in a crucible. Again, a little tiny porcelain dish here. And when the crucible's not hot, it's very easy to grab by, again, the tips of the crucible tongs, and the lid can be handled in the same way. Now, when it's hot, you might find yourself needing to scoop it up in the dents of those stems. So this is it takes some practice. Don't squeeze it too hard like I did just a second ago and send it flying across the lab. Try to practice gently picking these up. If the lid falls off, it's okay. You can always pick the lid back up, set it up upright. Okay, take some manipulation here, and then you can pick it up again. Having that hot hands as a backup is a good idea for this part. This will be placed into a clay triangle. The clay triangle is used when we're heating objects to high heat because it's, again, a porcelain, and so it's very capable of handling the heat of a Bunsen burner. So I would really recommend you practice. Try to get my hand nice and low. You can even set the crucible up on the base of your ring stand, and that allows your hand to get in underneath there. The key is to really not squeezing too tightly, just to gently rest it in the shape of the arms of the crucible tongs. Underneath the crucible, you'll be using a Bunsen burner. So for some of you, this may be the first time you've ever used a Bunsen burner. The Bunsen burners hook up via a hose to the gas jets on your lab bench or in the hood. So you simply push that onto the nozzle. The Bunsen burner is controlled by two methods. On the bottom of the burner is a dial or a knob that controls how much gas is allowed into the burner. This would just be the same as a gas stove, with a knob on a gas stove turning up or down the gas. The stem, the actual burner itself, turns on its base. And this adjusts how much oxygen is allowed in through the vent at the bottom, which controls the temperature of the flame. If you've used a gas stove, you notice that your flame is usually blue. That's due to the amount of oxygen that's reacting with the natural gas or propane, depending on what you would have. And so that is the signature color of that reaction. The more oxygen you let in, the hotter your flame will get. And you'll be looking at points during the lab today to create a cone within the flame that looks like a very sharp point blue tip. Now there might be another bit of flame going on around here. This is the hottest part of the flame, when you get that interior cone in your Bunsen burner. Don't worry about the shaft being too hot, especially down at the bottom. While the burner is on, you can touch, especially the bottom, and twist and turn it to adjust the flame to give you the desired flame that you're looking for. I recommend that you do this out away from your crucible, that you practice with it a little bit, and dial in your Bunsen burner to just the right value of the flame, or just the right type of flame, before you then place it here. Also, put some thought into where your iron ring is. I shouldn't need to put a lot of gas in to drive the flame all the way up to here. I can simply lower this down. Again, best done when it's not hot, so before you begin the actual process of heating up your crucible. A little bit of thought before you set up things can really make life go a lot faster, a lot easier in lab this week. This is the striker to light the Bunsen burner. The proper way to use this is, again, to have the gas flowing, but have this at the ready. Once you hear the gas, hold this at an angle above and strike. Simply draw it across the flint, and little sparks should emit and light the flame. If you're really nervous, ask for some help from the student lab assistant or the professor in the lab today. We'd be more than happy to help you get things started. But we want you to experience some of these things and learn how to safely set up and utilize this equipment for yourself. So again, I think today's goal is to find the empirical formula of your two ionic compounds, and to above all be careful while you do that. I wish you a good day in lab, and I hope you have good results.